Hey guys, welcome to my channel. On this video, I'll be solving a system of forces problem, which is part of the FE exam review series that I'm starting. So the problem states as follows. Beam AB has a distributed load as shown and supports at A and B. If the weight of the beam is negligible, the force RB is most nearly option A 24, option B 12, option C 10, and option D 8. All right, let's get started. So the step one will be to find the concentrated load. So we're given a distributed load, which is a triangular shaped distribution load of 8 kilonewton. In order to find the concentrated load, we will need to calculate we'll need to treat it as the area. We'll need to calculate it as the area of a triangle. So force is equal to 1/2 base times height, where the base is 3 meters and the height is our distributed load value of 8 kilonewton. So just gonna plug in this number on the equation. 1/2 times 3 meters times 8 kilonewton per meter. It's always important to ensure to include the unit to see how they cancel out, because sometimes they'll try to trick us with those questions where the units do not match, and if you jump into the solving the question quickly, you may not pay attention to that and end up finding an incorrect answer. So we plug in this number in the calculator. The force comes out to be 12 kilonewton. As we can see, the meter cancel out. So now that we've calculated the concentrated force, we would rewrite the beam in terms of that concentrated force. And since this is a triangle, we know that the concentrated force acts in the centroid of the triangle, which if you open up the FE handbook, you can just search for centroid, and here we'll see that the centroid, where you have your x-axis on the horizontal, is equal to 2/3 times the base. So getting back to our problem, 2/3 will be somewhere about here. So this is where our concentrated force will be placed. So now that we know that, we will redraw the free body diagram. So A, reaction A, B, reaction at point B, and 2/3 of 3 meters. So the concentrated force will be somewhere about here. So 12 kilonewton. So we have the 3 meters, and then 2 meters here, and then 1 meter. So now that we've done that, we are going to set the summation of moments at point A to be equal to 0. So summation of moment at point A is equal to 0. Only two forces that will be on the right hand of point A will be our concentrated loads of 12 kilonewton and the reaction at point B. So to calculate the moments, as we all know, is force times the distance. So the concentrated load being the first force times the distance to point A. Let's change some color here just so we can make it stick out. So we have 12 kilonewton times 5 meters, and this moment gonna be clockwise. So it doesn't matter what sign you choose as long as you stay consistent. Like for instance here, since we're choosing a clockwise moment to be positive, that means that a counterclockwise moment will be negative. That being said, we have 12 kilonewton times 5 meter, and force, the reaction force at point B, going to be counterclockwise, will yield a counterclockwise moment, so that will make it a negative one. So we'll have minus point B, the distance from point B to point A. Let me change colors here once again to make it stand out. So we have 6 meters from the reaction force B to point A. So that'll be minus 6 meters times reaction force B, and that should be equal to 0. Okay, so putting this number in the calculator yields 60 kilonewton meter minus 6 meter RB is equal to 0. 6 meter RB will be equal to 60 kilonewton meter, and we see how the meter cancel each other out. So RB will be equal to 60 kilonewton over 6, which gives you 10 kilonewton. And that is the answer to the problem. Looking back at our proposed answer, that will be the option C.